Started, I would like to start thanking the organizers for giving me the possibility to give this talk. So I will be talking about a couple of papers we wrote with Juan Maldacena, mostly about these two, some old work and something more recent things. So we will be mostly interested in computing gluon scattering amplitudes, or in general scattering amplitudes, in a very particular theory, namely planar n equals 4 super Unimills. Of course, in principle, one would prefer to compute the same quantities in QCD or large NQCD or some more realistic theory. But the reason why we choose this theory is first because we think that it can still give some non-trivial information about theories like QCD. But on the other hand, it's much more tractable. In particular, in the last years, many tools become available. And two tools will be particularly interesting for us. One is the so-called AdS CFT duality, or this duality between gauge and string theory, that allows to study the strong coupling limit of this n equals 4 super Unimills by studying a weakly coupled AdS, a weakly coupled string sigma model. On the other hand, perturbative computations are also easier, and higher loop amplitudes appear to have a remarkable iterative structure. And this structure actually has led to Bernd, Dickson, and Smirnov to a proposal for all loops endpoint amplitudes. So what we will try to do in this talk is to put these two things together and to give a prescription for computing gluon scattering amplitudes of planar n equals 4 super Unimills at a strong coupling by using the AdS CFT correspondence. The outlook of my talk is, first I will start by giving a brief introduction, telling what the gauge theory results are, but those were mentioned already in the previous talks, and then showing one slide and nothing else about this AdS CFT duality. Then we will set up the string theory computation, and then we will see how this prescription works in detail for the case of the scattering of 4 gluons. Then, if I have time, I will mention about this dual conformal symmetry and how this arises at a strong coupling. And then I will talk about this duality between scattering amplitudes and Wilson loops. And then we will see that we can use this duality to propose a test for this BDS conjecture. Finally, I will close with some conclusions and outlook. Please stop me at any time if you have any doubt, even if I don't tell everything that I want to tell. That is probably going to happen. I would like what I say to be understood, so you can stop me and we can discuss. So, okay, in the gauge theory, these guys, Bernd, Dickson, and Smirnov, but also together with other people, studied the so-called leading NC is the number of colors, color-ordered endpoint amplitudes. So the full amplitude is something like this, schematically, but in the planar limit, the color structure decomposes, and you can study these quantities here. We will denote by N, A, and L the amplitude for n gluons at L loops. It turns out that these amplitudes are divergent. You compute them and you get infinity. So we need to regularize them in some way. A very popular thing is to consider the theory not in 4 dimensions, but in 4 minus 2 epsilon dimensions. Then the amplitudes will be finite, but the price you have to pay is that they will depend explicitly on this parameter epsilon. What they have noticed, Bernd, Dickson, and Smirnov, and other people, was that if you scale out the 3-level amplitude and define a new amplitude, M and L, like this, is for n gluons at L loops, remember. So up to a few loops, each loop amplitude can be written in terms of lower order amplitudes. So for instance, how this works. For 2 gluons, for 4 gluons at 2 loops, the amplitude is roughly the square of the 1 loop amplitude plus a function times the 1 loop amplitude computed at a slightly different dimension, 4 minus 4 epsilon, plus some constant, plus some things of order epsilon. This kind of computations has led them to propose this very nice formula for MHV amplitude. MHB amplitude, like when you have a lot of gluons, means that n minus 2 gluons, that is a lot minus 2, will have some helicity, and the other 2 gluons will have the opposite helicity. So what they proposed was that the full amplitude was given as follows. So the way this formula works is as follows. This alpha is basically proportional to the Toff coupling constant. Remember that in dimensions different from 4, the coupling constant will be not dimensionless anymore. So we have some scale that will be some infrared scale. Then this alpha will keep track of the loop order that you are looking at. So if you want to know the amplitude at loop 20, you just expand this exponential and look for the coefficient of alpha to the 20. In particular, here we see this function f multiplying the one loop amplitude for n gluons plus this constant plus something that goes to 0 as epsilon goes to 0. Now, the content of this conjecture is just given by the fact that this function f and c don't depend on the number of gluons. So those are in the kinematics of the gluons. So they are just some numbers, this FL. So if you compute them by doing some explicit computations for, let's say, 4 or 5 gluons, then you have a prediction for any number of gluons, for the amplitude for any number of gluons. For us, will be very interesting the case of 4 gluons, so we will focus on that case. In that case, the amplitude will have 2 pieces, according to the BDS conjecture. We'll have a divergent piece and a finite piece. The divergent piece is characterized by 2 functions. One function, f, that basically f, that is nothing but the cusp anomalous dimension, controls the leading divergency, the piece proportional to 1 over epsilon squared. And then we have another function g, that some people call it, I think wrongly, some collinear anomalous dimension. It's not the anomalous dimension of anything, that controls the piece proportional to 1 over epsilon. In addition, you have also a finite piece, and it's very remarkable that this finite piece is also controlled by the same function f. And that is, I want you to remember this piece. So remember that the finite part of the amplitude for the scattering of 4 gluons contains a piece that is proportional to the log square of S over T. Here, S and T are the usual Mandelstam variables when you are scattering 4 particles. So, in order to study this system at strong coupling, these amplitudes, we will use the AdS CFT duality. I don't need to go into details in this conference. So it's basically this duality between the same gauge theory we were talking about for dimensional maximally supersymmetric Yang-Mills and tied to be a string theory on AdS 5 cross S5. As you well know, this duality provides us also with a dictionary between the parameters on both theories. So you see that the Toff coupling constant is related as follows to the radius of the AdS. That is the same as the radius of the sphere in string units. This means that you can study a strongly coupled gauge theory, let's say lambda equals to 1000, by studying a weakly coupled sigma model. Now we will use this duality to study scattering amplitudes at a strong coupling. First, we will proceed and set up the computation by using a D-brane as an infrared regulator. Remember that I told you that in the gauge theory, these amplitudes are divergent, so we will need to do, so at a strong coupling, the same will happen in the string theory. They will be divergent as well. So first, we will regularize them by introducing a D-brane, but actual computations will be easier to do in an analogous two-dimensional regularization. So some part of the result, yes. The point, I mean, there is 2 reasons why we choose this regularization. First, because we couldn't do the computation with the D-brane, of course. And then because, anyway, you want to compare with gauge theory results. And the BDS conjecture is mostly put, I mean, Bernd-Dixon and Smirnov used dimensional regularization. But you will see which, I will tell you exactly which part of the result should depend on the regularization and which part shouldn't. hopefully. Yeah. So, okay, so let's set up the computation. So I told that the thing we need to consider was strings on AdS5. Here we see the AdS5 metric in point-caret coordinates. And then what we do is we introduce a d-brain that will be extended along these 3 dimensions and located at some finite but very large c equals c infrared. The boundary of this AdS is at c equals 0. Now, once you put the d-brain, you have asymptotic states that correspond to open strings ending on this brain. So what we will do is we will consider the scattering of these open strings. Notice that as the proper momentum of these strings is very large due to the fact that our space is warped, so here you can compute the proper momentum and you find that this k is the conjugate, the momenta conjugate to this x. And then you need to multiply by this factor c infrared over r, and remember that this c infrared is a very large number. So this proper momentum is very large. So actually what you are considering is the regime of fixed angle and very high momentum. Fortunately for us, there is such an example of this kind of computations in flat space that was done by Gross and Mende many years ago. And the key feature of this computation is that the amplitude is dominated by a saddle point of the classical action. So all what we need to do is to consider classical strings on AdS. That is all the computation boils down to consider classical strings on AdS. So for instance, for the case of, so what we will need to compute will be a worksheet with the topology of a disk that will have vertex operator insertions, here you see 4 for instance, that will correspond to the external states that you want to scatter. Then you will have some boundary conditions, and the boundary conditions will tell you, for instance, that near each vertex operator, the momentum of the external state will fix the form of the solution, and on the other hand, the open strings are ending on the d-brain. So the worksheet will have the boundary located at c equals c infrared. Yeah.
But you really want to compute the amplitude strong coupling for fixed momentum. So the reason why you're taking minimum of the actions is that's the reason, not as a cross.
Well, no. What I am telling is that the classical action will be a good approximation to the amplitude, because the proper momenta of the strings is very large. Here, what is fixed is this momenta k. Not
about string tension. What about?
Well, the lambda will be large. Yeah.
It is kind of an important question, because the question is, what do you do if you send lambda to infinity to justify semi-classical approximation of string theory, or infrared regulator to 0 to infinity?
Yeah, that's a good question. You have to be a little bit careful, but you see that you can do both things, keeping having the fact that the classical action is a good approximation. I think saddle point is even more robust in AdS than in flat space.
What is the sequence of the worksheet?
Oh, now you will see. Will be Euclidean mostly. Okay, so now these boundary conditions look a little bit obscure to us, and also one of the problems was that in the Gross-Mende the solution had an eye, was purely imaginary, so we couldn't plot it in Mathematica, and we didn't like this feature. That was our main motivation to go to the so-called T-dual variables. So we have these variables, and we define, I just put it between quotation because these variables are non-compact, the x coordinates. But we do T-duality anyway, defined by following the usual Basel rules. And then the boundary conditions translate as follows. If x mu carries some momentum k mu, y mu will have some winding delta y mu. And that will be a little bit more clear in the next transparency. What is nice is that after a change of coordinates, c goes to r squared over c that we call r, then we end up again with exactly the AdS5 metric. Now, we have what happened with our worksheet. The worksheet will have its boundary located at r equals r squared over c infrared, and it's a particular line that is constructed as follows.
Why is delta y related to k?
Well, now you will see exactly what I mean by this. But k is the initial momentum. You know, in this T-duality, you interchange momentum by winding, and vice versa.
It's on real T-duality, you say it's just a change of variable.
Well, I will then exactly tell you what I mean by winding. Yes. So maybe let me tell you how the worksheet will look like. So we have a worksheet whose boundary is located here at r equals r squared over c infrared, and will be a particular line that is constructed as follows. So for each particle of momentum k mu that we want to scatter, we draw a segment that joins 2 points separated by delta y mu equals to 2 pi k mu. So each of these lines represents an external gluon that I want to scatter. Then we concatenate the segments. We put the segments one after another according to the ordering of the insertions in the disk. Now, as we take the infrared cutoff to infinity, this C infrared to infinity, then the boundary of the worksheet moves towards r equals 0. So the computation that we have to do is exactly the same computation as you would do if you want to compute the expectation value at a strong coupling of a Wilson loop given by such sequence of Lilay segments. So our prescription, what we are telling, is the following: is that the leading exponential behavior of the endpoint scattering amplitudes is given by the area of the minimal surface that ends on a sequence of Lilay segments on the boundary, and these Lilay segments are given by the momenta of the gluons. Notice, for instance, that due to momentum conservation, this will be a closed diagram. This is the time direction, y0. So each of these segments is Lilay. So by this relation, if you give me some gluons that you want to scatter, you tell me what the momenta of the gluons is. I draw these segments, this polygon, and then the area of the minimal surface ending there will give you the scattering amplitude at a strong coupling. Is there any question before I proceed?
Where's the sort of supersymmetry stuff floating about? I mean, in principle, you can have any AdS space so far.
That's true. You don't see it at a strong coupling. Yeah. By the way, yeah, related to your question, notice that prefactors, for instance, having to do with the helicity of the particles, will be subleading in 1 over the square root of lambda. In particular, it may be that this prefactor is 0 for some kind of amplitudes. And notice that this is also insensitive to the fact whether you are considering a MHV or non-MHV amplitude. Now,
The result is universal and the same for any gauge theory that has a
conformal, yeah,
level.
yeah, I would say so, yeah. Of course, at leading square root of lambda, but the prefactors can be very complicated. Okay, now let's see how this, all these are kind of words. Let's see how this works for the case of 4 gluons. So, in the case of 4 gluons, you have 2 guys, 1 and 3, going into 2 other guys, 2 and 4, and we define the usual Mandelstam variables. Then, in that case, the diagram, the polygon will look like this, and what we need to do is to find the minimal surface that ends on this polygon here. It's not so hard to write the Nambu-Goto action, so the easiest way is first to use Poincaré coordinates that are given by this, r, y0, y1, and y2, and then parameterize the surface by its projection to the y1, y2 plane, to this plane, to the plane parameterized by y1 and y2. Then all what we will have is an action for two fields, r and y0, that will live on the space parameterized by y1 and y2. For instance, if S is equal to t, then this will be a cube, and the projection will be a perfect square. So the Nambu-Goto is as follows, and then we need to supplement the equations of motion coming from this action with the boundary conditions. For instance, for the case in which S is equal to t, we will have a square, as I just told you, and by scale invariance, we can put the edges of the square at plus minus 1. Then the boundary conditions will be that the field R vanishes in the edges, plus minus 1, and then the field y0, that is time, has to go up and down, as you move along the edges.
Don't you violate scale invariance by the regulator?
Which regulator?
Well, you'll put a D-ray.
I mean, for the moment, I am not doing anything.
Okay.
And then we will see how this will come. Yeah, but for the moment, we are not regulating. And remember that we took C infrared to infinity. And now we have this problem. Anyway, I mean, you have an equation of motion and boundary conditions. Why would you want conformal invariance anyway?
Well, what do you mean by scale invariance?
I mean, what I mean, if you find the solution to this equation, then you can put simply a here, and you will have a solution for the square with other. Anyway, as we took C infrared to infinity, we have conformal invariance anyway, right? It's just a trick to have a simpler solution. But OK, so you have these equations of motion. There is unfortunately not a systematic way of solving them. So the only thing you can do is to try some ansatz. And the first thing we tried, it just worked it out. So you see that this satisfies the equations of motion and the boundary conditions. So OK, perfect. That is the surface we wanted. Great. However, notice that the log of 1 is equal to 0. And like the most interesting, one of the interesting parts of the amplitude was this piece proportional to log square of S over t. So this is the solution for the case S is equal to t. So it's somehow a boring case. OK, we were like trying to figure out what to do for 1 week. And then notice that if S is different from t, the projection will not be a square anymore, but will be a rhombus. And the distance between these two vertices is basically proportional to square root of t and square root of S. So, OK. So one nice thing that you can try to do is to change coordinates. Like usually helps to change coordinates. So for instance, if you write the solution, instead of in Poincare coordinates, you can choose to write in embedding coordinates. So in this, you embed AdS 5 in R2, 4, and the relation to Poincare coordinates is this. So in embedding coordinates, the surface is only this. And at this point, we don't have a regulator, so we have conformal invariance. So we notice that if we perform SO2 transformations, starting from one solution, we can get other solutions. In particular, there is, if you apply a boost in the 0,4 direction, you will have a new solution that has S different from t. One can explicitly check that there are conformal transformations on this SO2, 4 that change the distance between these two vertices. Now, you should not confuse this SO2, 4 that has to do with this AdS 5 space with the original one. This came just after we did the T-duality and this transformation.
So in terms of the original variables, it would be some non-local?
It will be very ugly. Yeah. Yeah, exactly. Will be indeed.
But it would be some consort integral or something like that?
Yeah,
what would generate this transformation?
It will be something something non-local, I guess. Yeah. But it's not very nice looking. So, okay. So first we had now two parameters. We have one parameter that has to do with this boost, and another parameter that has to do with the dimension of the original square. So at the end of the day, we end up with a solution. I have chosen to write it in conformal gauge, and that is the only equation with 3 lines that I will show in this talk. We choose to write as follows. So this solution, we see that depends on 2 parameters, A and B, that encode the kinematic variables S and T, the Mandelstam variables of your problem. Very good, nice. So we got the solution. Now we can take the solution, we can plug it into the action, and we can get the amplitude of the strong coupling. Well, it's not so fast because actually the area diverges. So actually it's pretty funny that if you plug this into the action, you get 2. And you have to integrate 2 between plus and minus infinity. Of course, that was to be expected because we took the infrared regulator to infinity. So we don't have a regulator anymore. So the amplitude was going to be divergent, unless we did run the computations, but it's okay. Now, what does people do in gauge theory? So what they do, I told you roughly that they consider the theory in 4 minus 2 epsilon dimensions. More precisely, they start with n equals 1 in 10 dimensions, and then they dimensionally reduce to 4 minus 2 epsilon. But that is exactly, if this d were integer, the theory that lives on a dp brane, if p is d minus 1. So what we do is, instead of AdS 5 cross S5, we consider the near horizon geometry of a dp brane, and we simply say that p is 3 minus 2 epsilon. So we do this kind of analytic continuation. If we do that, then we can proceed exactly as before, but now we see that our action will be exactly as before with this extra 1 over r to the epsilon. So it's a little bit misleading to call it this epsilon because this epsilon is negative. So you could have called it minus epsilon. But then, okay, we get this. Now, the presence of this r to the epsilon has 2 effects, a good one and a bad one, of course.
Can I ask a question before we proceed?
Yes.
Do you substitute the original undeformed solution for this?
I will come to that.
Okay.
Yeah, that's a very good question. Now, of course, there are 2 effects, a good one and a bad one. The good one is now that the integrals will converge because you have this r to the epsilon. The bad one is that the action depends on epsilon, and also the equations of motion will depend on epsilon. And we were not able to solve the equations of motion for generic epsilon. However, it turns out that we are not interested. Of course, we would be interested, but since we cannot compute it, we say that we are not interested in knowing the full action, but we want to know only the action up to terms of finite order as epsilon goes to 0. And roughly, up to this 1/2, it is enough with taking the original solution and plugging that into the corrected action. If you do a little bit better and you have into account, to answer to your question, what the solution is close to the cusp for generic epsilon, then you get this extra 1/2. But will be not that interesting for us. Okay, so you plug the original solution into the corrected action. After a couple of days of trying to do the integrals, you come out with this result here. Okay, that's it. So now we can get this. We can express this b in terms of s and t, and we can expand in epsilon. So that is our final answer. So this final answer is to be compared with the field theory answer, or better to say the field theory prediction or proposal by BDS. So first we see that the structure is very much the same. We get a piece proportional to 1 over epsilon squared, a piece proportional to 1 over epsilon. If you use the strong coupling result of this cusp anomalous dimension, this coefficient is exactly what you would expect. besides from this computation, you can get the strong coupling value of this function g as well. And even more interestingly, we get exactly this log and ln are the same function. Sorry for that. You get exactly the same coefficient once you use the strong coupling result. So for the case of 4 gluons, our computation agrees exactly with BDS. Yes?
Isn't there subtlety? I mean, if you would shift your scale u, right, this would affect the 1 over epsilon term.
That's true, indeed.
So you don't really, you can't really say you have a prediction of strong coupling of the collinear numbers.
Okay, that's true. I mean, what you can say is exactly that. If you take G as Bernd-Dixon and Smirnov define that G, then for that function, if you are very careful that you are using the same regularization, then you can say that you can follow that function from weak coupling to strong coupling. Now, whether this function has some physical meaning or not, that is another question. I think it doesn't, due to the fact indeed that you can shift this G always by a constant. So what we are saying is that this G is as Bernd-Dixon and Smirnov define it, is the strong coupling limit of that G. And that answers also to Sergei's question of asking what is scheme independent and what is scheme dependent. So this function f and this constant c get shifted as you change mu to 2 mu for this. Okay. Notice, I have like 10 minutes. So first notice that SO2,4, I will quickly mention this. Notice that SO2,4 transformations fixed somehow the kinematical dependence on the finite piece. Since to restore this S over T dependence, we needed to do transformations. On the other hand, a question we can ask, is dimensional regularization so important? And actually, to do this regularization is important just to get this function g. So this function g indeed will depend on the regularization. Another computation that you could try to do is to take the original solution into the original action, but then cut off the integrals. It's a messy computation actually, but at the end of the day, you can come out with this area, and quite surprisingly, the finite piece is exactly the same as the finite piece that comes by using dimensional regularization. So up to some constant that is independent on the kinematics, we get the same finite piece. Now, we can do a little bit better, and now some assumptions come, and we can imagine that the cusps are located at some points xi. This xi will be the same that of today's talks. And now we can imagine that the cutoff, instead of being a constant cutoff along the loop, depends on the point of the loop. So if we suppose that the amplitude will have this form, that this will be the divergent piece, and this will be the finite piece, notice that here we are supposing that this divergent will depend on the value of this cutoff only at the cusp. But at a strong coupling, having the solution, that is something that in principle can be checked. So now these SO2,4 transformations, the only that we'll do is to move these points xi and ri, and the area should be invariant under this transformation. So notice that of course, it's quite surprising that if you consider this generator, this is just one of the SO2,4 generators written in point correct coordinates, you get exactly the same equation as Drummond, Korczynski, Sokachev, and Hen were talking about. So this anomaly term comes when you act with this Ri, dri on these pieces. But of course, there is many suppositions I am making, so those need to be proved. So, okay, in the last minutes, now the computation we have done shows that there is some relation between Wilson loops and scattering amplitudes. This relation is, we have seen today, that holds also at weak coupling. So precisely, what I mean is the following. Suppose that instead of BDS, you write the log of BDS, and you consider the amplitude for n gluons. Then you will get a divergent piece that we don't care about, plus the one loop expectation value times the cusp anomalous dimension. This is what BDS is telling to you. Plus two functions that will not depend on the kinematics or the number of gluons, and we don't care about. Then, if you compute the expectation value of the scattering of a related Wilson loop, the Wilson loop that you hear today, you see that at one loop, you get this function W1. And these guys have noticed that this W1 is equal to this A1. So this is a one-loop computation that you can compute these two quantities, the scattering amplitude, the expectation value of the related Wilson loop, and you can see that they all agree. So summary of the results. So first, I told you about the BDS conjecture. What the BDS conjecture is telling to you is that the amplitude at a strong coupling, by the amplitude I mean that finite piece that depends on the kinematic of the gluons, is equal to the cusp anomalous dimension at a strong coupling times the one loop amplitude. On the other hand, the strong coupling computation that I just told you about tells you that the strong coupling amplitude is equal to the strong coupling expectation value of the Wilson loop. And these guys have shown that at one loop, the two quantities coincide. So we get these three equations, we plug them in Mathematica, and we come out with this equation. So the expectation value of this Wilson loop at a strong coupling is nothing but the expectation value of the Wilson loop at one loop times the cusp anomalous dimension at a strong coupling. And it turns out that for the case of 4 and 5 gluons, that is the case. But we have seen that for 4 and 5 gluons, this was fixed by symmetries, by this dual conformal symmetry. So in order to really test BDS, we need to consider more than 5 gluons. So what about considering an infinite number of gluons? And what we do is we choose to consider, because if BDS is right, it should be right for any configuration you can think of. If you just think about one configuration for which BDS fails, then you are just disproving it. So what we choose is to consider a zigzag configuration. Here, this is the time dimension, and here these two are two spatial dimensions in which we approximate this rectangular Wilson loop by a lot of zigzags. This is exactly the same Wilson loop as people consider when they consider the static potential between quark and T-quark in n equals 4. So in that case, we could just see at the papers, and we could see that the term proportional to T over L was computed. This is a weak coupling, this is at a strong coupling, and the coefficient is not what you would expect from the BDS ansatz. So something needs to be revised.
Are they right-angular zigzags? The
Sorry,
zigzags are 90 degrees?
These are all lilac.
Yes.
They have to be lilac, and they have to be cusped. No, yeah, yes. Okay, so BDS, at least for a large number of gluons, by large number of gluons I mean at least 6, but maybe 22 gluons, needs to be revised. So I am just jumping, no, that's fine, to the conclusions. So what have we done? We have given a prescription for computing planar scattering amplitudes at a strong coupling of n equals 4 super n mil at a strong coupling by using this AdS CFT duality. We have done some detailed computations for n equals 4, but the prescription is valid, n equals 4 not supersymmetry, but number of gluons, but the prescription should be valid for any number of gluons, and we expect our results to agree for 4 and 5 gluons, but the conjecture, the BDS conjecture, may need to be revised for more than 5 gluons. And hopefully this is a small step towards understanding these iterative structures from the point of view of string theory. So what has to be done? Well, a lot of things, yeah. Unfortunately, I had this list and it increases, but I never solve the problems I want to solve. So first, of course, one needs to try to make explicit computations for more than 4 gluons. And for instance, 6 gluons would be a very nice example. Then I was going to tell you how to use integrability to compute this, but I didn't have time, unfortunately. No. So notice that we haven't assumed or used at all the machinery of integrability. But strings on AdS5 are an integrable system, we hope at least. So hopefully in the future we will learn how to use integrability in order to solve for these amplitudes. Then subleading corrections in 1 over square root of lambda are also very interesting. They will give like information about helicity, for instance. Gross and Mende computed also higher genus amplitudes in flat space using pretty similar ideas. It would be nice to do the same here. Then it's interesting the question whether we can repeat the same computation in other backgrounds, like black hole backgrounds, for instance. Then we would need to understand if there is any deeper relation between Wilson loops and scattering amplitudes. And finally, if BDS is wrong, that I think probably is wrong, then whether we can find some alternative to BDS conjecture. Thank you very much.
Yes. What about point 2?
We haven't assumed use.
What do you want to try?
So for instance, okay, I can tell you. So, I mean, one of the hopes, there are 2 different, I can think of 3 different directions actually. So the first thing would be to try to apply this inverses of this dressing method. And you know that you start with, well, of course you do not, but you start with one solution and then you can generate a lot of other solutions. So it would be nice to start from the solutions we have and somehow to get with this Backlund transformation or whatever the solutions. That was tried by the group at Brown University. And well, they were not quite successful, but okay, that is, I think, a very good idea. Another idea would be to know the value of the action even without knowing the value of the classical solution. So I think that would be basically, I mean, one may hope somehow that to be able to compute the action even if you don't know what the classical solution is, just by giving the boundary conditions. You could try to construct a connection for this kind of solutions and then try to see if you can find the action. So, yeah.
Do you mean you want to use the machinery of classical integrability?
Yes, yes, for the moment classical, yeah, indeed. I mean, just to know them at strong coupling, just at deeper strong coupling. Then I could think about, yeah.
For this finite term, at least at 4 point, it just depends on S over T.
That's true.
So I could choose S equals 0 and T equals 0. Does anything simplify in that?
Oh, I see. Well, how? Yeah, it's a little bit tricky to choose S and T very small.
So I'm thinking that, you know, that in 4 dimensions you can write null momentum as pi times pi bar.
Mm-hmm.
And when S and T equals 0, you could choose all the pi's the same. Right?
Of course, for instance, you have to be a little bit careful because, I mean, since you can solve everything for S and T arbitrary, in principle you don't need to choose. But on the other hand, remember that for the classical solution to be a good approximation, this quantity has to be large. So that is for any k finite but different from 0. So some people attempted, for instance, to study something like the Regel limit. So the Regel limit is a limit, for instance, in which S is much larger than T. So, I mean, when you write the amplitude in this term,
I wasn't thinking K.
but when you are writing the amplitude in this, you think that this mu is the infrared regulator and it's much smaller than this S. So you shouldn't be allowed to take S of the order or smaller than mu. So we are thinking about S and T some number, like some finite number. But maybe, I mean, doing some OPE, then maybe you can.
So since you mentioned the Regel limit, I wanted to ask you if one is supposed to understand that there are trajectory in a regulated theory that could collapse one on the top of the other to give other things when you remove the regulator. Is that so?
I mean, in principle, what we did should not be valid for that regime. So one could study anyway. And maybe like what you may expect, for instance, is that in that limit, for instance, you have many classical solutions, right? Or something like that. You may hope to study something like that, but I haven't thought about that, to tell the truth. But you have to be very careful with the limits you take. In principle, this S should be much larger than mu, S and T.
So let's assume that your zigzag approach to the large N limit for gluons is correct, and that you rule out the explicit form of the BDS conjecture.
Mm-hmm.
Now, so I think what's important about the BDS formula is not its precise form, but the fact that they have seen an iterative structure. In other words, something simple has been iterated or exponentiated. So would it be correct to say that you are not only saying that the BDS form should be different, but that it doesn't look like exponentiation of anything which is one loop like? Didn't you say in your paper somewhere, in your last paper is one, that this log of Wilson loop doesn't, that the two loop correction doesn't look like it comes from exponentiation of one loop?
Okay, yeah, exactly. That is, okay, I think there are two, but if you want to say something, okay, just let me, one for you to understand the answer. So the point is that these three equations here, BDS tells you this, but also tells you that A at two loops should be the cusp anomalous dimension at two loops times A1, right? So you have this equation. Then, on the other hand, this was proven, but if this duality between Wilson loops and scattering amplitudes is true, you could write the same equation with a 2 instead of a 1. And now you could put these three equations and you would find that W at two loops is equal to the cusp anomalous dimension at two loops times the W at one loop. And that, for this zigzag Wilson loop, does not seem to be the case. So what may happen is that the duality between Wilson loops and scattering amplitudes doesn't work, or the BDS conjecture is wrong. So I don't know which one of the two. I think in any case, for 6 gluons at 2 loops, something. So what we are saying is that one of these two things will fail at 2 loops.
But it's strong coupling, right? Your own argument seems to be a pretty powerful indication that at strong coupling, the Wilson loops should reproduce the amplitudes at strong coupling. Mm-hmm. And then you're saying that, well, basically, as soon as you are saying that the BDS formula isn't right, it's not only saying that the specific formula isn't correct, but somehow no exponentiation.
Well, I don't know. In principle, you could add some things of order that starts at 2 loops, right?
Right, in that expression, in the exponent, right? And then
or at 3, at 4.
And the usefulness of this type of formula in field theory would be lost.
That's true. That's why
you would say that in order to calculate, let's say, the two-loop result, I actually need to know it.
Exactly. That's what I mean by this powerful here. That it would be nice to find some alternative to BDS, but BDS is pretty powerful. For instance, let's take this non-abelian exponentiation theorem. It's okay, it's nice, but it's not that much powerful because at each loop order you have to compute diagrams anyway. So I have nothing to say whether this BDS will be the exponentiation of something finite, I mean that ends at 10 loops, or maybe it's not an exponentiation at all, or maybe, I don't know.
On the string theory side, you calculate classical action.
Yes.
Can you comment explicitly how do you see on the field theory side that at some point classical limit was taken?
Oh. No, I don't know. I mean, are like two opposite regimes, I think.
So when you take large coupling in Young-Mills, it's equivalent to taking classical limit in some sense?
Yes.
Can you comment why?
Well, no more than, I mean, they are proposing some expression for the amplitude, that should be true for, I mean, suppose this alpha L, FL, you write as some function f, right? And this times this, you write as some function c. So what BDS is telling to you is that that expression should be true for all values of the coupling constant and all number of gluons. So in particular, when the coupling constant is equal to 300, you expect supergravity to be a good approximation by the usual AdS CFT law.
But
There's no large charges. So I don't see
well, maybe it sits on some master field.
I mean,
For a
suppose,
Menday argument. I mean,
yeah.
large momenta in your scattering, in your string scattering.
Yeah. Okay, so yeah, here, exactly. Here we use just the observation that if these quantum numbers are large, then the classical action is a good approximation. But notice that these k, that are the gauge theory momentum, don't have to be large. So in this formula, S and T, etc., they don't have to be large. The classical action will be still a good approximation if lambda is large.
I would give a slightly different version of this explanation, which though in your case is equivalent. There is a square root of lambda Toft in front of the string action. So square root of lambda Toft going to infinity makes, well, gives you a semi-classical regime in string theory.
Yeah.
And it's a strongly coupled regime in field theory.
well, there's some cases where there's classical involved.
In
Yeah.
this case,
Yeah, but not here. It's important to say that for the gross and Mende computation to work, these Mandelstam variables has to be large. But here they are any number. S and T are any number. So in this amplitude, sorry, in the BDS amplitude, S and T they don't have to be large. You just take lambda large, and then string theory is a good approximation.
Any more questions? Okay, one more for Archive.
No, the comment related to the question. So at one loop, this is this Queen Mary prescription for this endpoint amplitude.
Yes.
It does remind well, it's related to the area. You may try to interpret it as if it should be the area.
Yeah, that's true. You might try. I tried to make that more precise, and I failed like miserably. But yeah, that's they look very much.
Must be somehow related to the next amplitude.
All right, let's thank the speaker one more time.